Decades of Mars research from previous spacecraft have shown the planet not only had water in the ancient past, but had environments that could have supported life.
Mars is our neighboring planet and in many ways the most similar to us, and certainly in its history. And the question whether ancient life was there is still the question that keeps us up at night.
Mars 2020 has two new objectives: to specifically seek the signs of life and then sample materials and prepare a cache that could be returned to Earth by a future mission.
Mars 2020 is really the essential first part of a sample return mission. So it actually looks at the environment of these samples and then collects them and stores them. Afterwards, we will of course go and bring these samples back. So Mars 2020 is the first half of a return trip.
The Mars 2020 mission, to the maximum extent possible, follows the Mars Science Laboratory Curiosity mission. We're going to use very similar rocket, very similar cruise stage, very similar entry, descent, and landing. And the rover, when you step back, will look almost identical.
Not only were a lot of designs already developed for the most part, but we're also using a lot of spare hardware that we had from MSL or Curiosity for Mars 2020. If you know where to look on Lab, you can walk around and see a lot of the EDL hardware and the cruise stage hardware that's already been built.
And this is really important for understanding why this mission makes sense. We have to do relatively little in the way of new development. And this saves money, it saves risk, it saves time. It's the right way to pursue this kind of mission.
Mars 2020 also features new technologies for entry, descent, and landing, allowing it to target a smaller landing zone and even divert from known risks in the area.
It means that we can both go to places that are maybe more interesting to the scientists because we're able to handle places with more hazards, as well as land closer to the things that they're interested in off the bat. So we get to the science that they care about and more quickly.
The three key sites that we are considering right now share one thing in common. They are all environments that might have been habitable in the very distant past. One of them is the floor of an ancient lake. Another is a hot spring. And the third one is a site where hot water interacted with rocks in the shallow subsurface. We have instruments on board which are expressly designed to seek evidence of ancient life, what we call biosignatures. And we have the capability to prepare samples, drill them out of a rock, seal them in a tube so that a future mission could go and bring them up. We call that caching.
So it is a first of a new type of mission, which is to bring samples back to the best labs we have, which are here on Earth. Mars 2020 is a pivotal mission in our search for life that could finally answer the age-old question, are we alone?
Good afternoon. My name is Dwayne Brown with the Office of Communications, and welcome to NASA headquarters. NASA continues its journey to Mars, and today you will hear the payload that will fly aboard NASA's Mars 2020 rover, a roving laboratory that will study the red planet as never before.
This is a really exciting day for us. We are exploring Mars right now with our Curiosity and Opportunity rovers, and today we're going to announce the complement of instruments that are going to fly on our next big leap in the exploration of Mars, the Mars 2020 rover. The Mars 2020 rover is really going to build on the science and the exploration we've learned from the Curiosity rover and all the other activity at Mars. And I think it's just amazing to think about the fact that Curiosity has determined that Mars once had a habitable environment. And the science behind the Mars 2020 rover is really going to extend that, and Michael Meyer will talk more about it, in our exploration of looking for potential biosignatures, of answering that big question, was there ever life on Mars, as part of our quest to understand if we're alone in the universe. This rover is going to carry new innovative instruments like we've never seen before on Mars to conduct geological investigations on the surface of Mars to determine potential habitability, but also to look for potential signs of past life in the geological record. These advanced instruments, however, carry a little bit of risk, and I think that's just part of the activity at NASA, that unless we try hard things, we're not really going to get the really great science that we need to get from the surface. It's even possible that with the Mars 2020 rover, some of the rocks that we interrogate look so intriguing that we will just absolutely have to bring them back to Earth someday to use the best instruments available on Earth to determine whether these are signatures of life. And so in the rover will be a small caching system to enable either future explorers or future missions to bring back those samples. Another great thing about the Mars 2020 selections that we'll talk about is it's a very international partnership, and we're really thrilled to have those partners on board. This Mars 2020 rover is a big step for NASA, significantly expanding our partnership between the mission directorates, and with a part of the rover including something that Gurst can describe between the Human Exploration Mission Directorate, Science and Technology. And it's really that glue between all of our activities that are making this our next big leap to Mars. And with that, I'll hand it over to Bill Gerstenmaier.
Thanks, John. It's my pleasure to be here. It's great to see the mission directorates really work together, to see Space Technology Mission Directorate, to see the Science Mission Directorate and our own directorate really work together on this mission. And it's neat to see that the synergies and the activities come together and work together. As John described, they're very interested in looking at Mars as a scientific investigation and trying to answer those hard questions. You know, is there life on Mars? Those kind of things, and building off of the other robotic activities. But then to let us on the human side come alongside them on Mars 2020 and bring some new technology to us from the Technology Mission Directorate that'll help us with our plans to take humans to Mars someday in the future. So we get a chance to look at things like in situ resource utilization. We look at the ability to use some of the resources on Mars to see if they actually have applications for human missions in the future. And those will dramatically change how we plan and get ready for those missions. We'll also get a chance to look at the environment of Mars, kind of from a dust standpoint and from a weather standpoint, and understand, again, are there implications for that we ought to be putting into our plans now as we begin starting to think about how we would actually move humans to the surface of Mars. So what a great time to see all these mission directors come together to work on the new technology we need to actually provide information for us on the human directorate side that we can use for Mars. It builds off of what we've done with Curiosity rover, with the entry, descent, and landing activity we did and the radiation monitor on Mars. We've kind of taken that to the next step, and we're actually moving together even with a broader cooperation and more activities together. So as we move forward, I can't think of a better way to keep working with these guys, and we're really on this journey to Mars. So with that, I'll be quiet and I'll turn it over to Mike, and he can give us the details of what's exactly on the rover and what's coming forward. So
Thanks
Mike.
so much, Bill. Actually, before we start, what I'd like to do is some of the project is represented here. We have the project manager, John McNamee. We also have the project scientist, Ken Farley, and also the program scientist, Mitch Schulte. So any questions I can't answer, I'm sure they will be able to. This has been an interesting process. 13 months ago, we received a report from the science definition team that basically said the next mission to Mars ought to do these things. And it had 4 major objectives: to go to a region, look at the geology, understand the environment, look for biosignatures, since there's a potential for life, cache samples for potential return, and make progress toward human exploration on Mars. It was kind of a tall order and quite a list of measurements that needed to be made. And I just want to say now that through the open competitive process, we've been able to put together a great payload that actually meets or exceeds all the measurement requirements that this science definition team laid out 13 months ago. So I'm surprised and happily surprised. So let's get down to it and talk about the instruments themselves. So if I can have the first graphic. One of the constraints of doing this mission is that we have this fantastic rover that's already designed. And so the instruments that go on the rover have to be able to fit within the spacecraft itself. And so there are volume constraints, mass constraints, and that sort of thing. And the good news is that we're able to select 7 instruments that address the 4 goals I mentioned. And so what I'll do is I'll go through them in kind of a counterclockwise way, starting with instruments that are on the mast of the rover. There's 2 of those. And then there's 3 instruments in the body of the rover, and then out on the arm are 2 more scientific instruments. So let's start going through them. On the mast, next graphic, we have Mastcam-Z. This is a multispectral binocular imager that has fantastic zoom capabilities. And so this will be on the rover, 12 different wavelengths or filter wheels on it to do multispectral, multicolor. The zoom capability is what's new to this camera. And the zoom capability, what it does, it makes it possible to rapidly develop terrain models so that you can plot your path and efficiently travel a longer, safer distance on Mars. So this will really help with mission operability, besides just being a fantastic camera for giving us panoramas and close-ups. The next graphic, the other mass instrument is SuperCam. It's actually a proper name for this amazing instrument. On Curiosity right now, we have an instrument that's called ChemCam that does laser-induced mass spectroscopy. What it does is it ionizes a little bit of a rock, and you can tell by looking at the plasma what the elemental composition is. This instrument takes that capability and goes much further, and then it's also incorporated a Raman spectrometer, which can identify minerals, and also visible and near IR spectrometer, which also can do minerals. So it now has an added capability besides having sort of a telescope on it that it can look up close to materials that it's zotted with its laser. So this makes it a tremendously useful remote sensing instrument where you can now look at things before you, rocks before you, and understand the elemental composition and also the mineralogy and make some informed decisions about whether or not a particular rock is important. And added to that is also the capability to detect organics. So this is tremendous for going forward to helping the mission plan on where to take the real samples, that sort of thing. Okay, so now we're going to move to the body of the rover. Then if we show the next graphic, this is MOXIE. This is the Human Exploration Operation Mission Directorate and this Space Technology Mission Directorate contribution of being able to take Mars atmosphere, take CO2 out of the atmosphere, break it apart, and produce pure oxygen. So this is going to be extremely useful for future rocket fuel from Mars, or when we have humans exploring Mars, they can also make great use of that oxygen. We all love that stuff. So this is a real step forward in helping future human exploration of Mars by being able to produce your oxygen on the surface of Mars. The next graphic, this is the Spanish contribution of a weather station, and it has things that you would expect, such as temperature, humidity, wind speed, but what's some other, and pressure, but also it's going to be able to characterize the dust and also look at the environment, the temperature of the surrounding environment. And so this gives us a very good idea of what's going on in weather-wise on Mars, and it helps for future exploration. But also, it'll be important to understanding how well our Mars oxygen experiment is doing, MOXIE, how well it's working by also making atmospheric measurements that help inform that efficiency. Okay, so in the third instrument, next slide, showing what's on the rover body. This is RIMFAX. This is a ground-penetrating radar. This has a very interesting capability of being able to penetrate maybe down to half a kilometer beneath the surface with a resolution anywhere from 5 to 20 centimeters. So we're going to get a look for the first time in the subsurface with a rover of the areas that we're traveling over with this instrument. And one of the interesting things is that then you'll be able to connect different outcrops that you see to see whether or not something that looks similar on one end of a basin versus another, whether or not it's actually the same geological unit by being able to trace it with your ground penetrating radar. Okay, so now let's move to the rover arm, where we have two instruments. One is Pixel. We see here an image of the sensor head. Fits in a box, fits on the rover head. If we go to the next image, this is what it does. By doing the X-ray lithochemistry, it can map out the element distribution of any of the image that it's looking at, the rock that's looking at, and put it on an image. So what this does is give you the interfaces, gives you the fine scale mineralogy. It tells you where the action is on the smaller scale. This is the scale at which actually life is, microbial life is concerned. And then the last instrument is Sherlock. This is a deep UV Raman luminescent instrument. And so using this, you can get fine scale mineralogy, tells you what the minerals are, and also detect organics. So if we go to the last slide, we have a fantastic grouping of instruments where the selection of the instruments were to maximize the science capability of the rover itself. Not necessarily any one instrument is it's great, but it's how they play well together. So one of the interesting situations of how this is set up is no measurement, such as elemental chemistry, is done by only one instrument. No measurement of mineralogy is done by only one instrument. And no detection of organics is only done by one instrument. They overlap and they complement each other. They look at the measurements in slightly different ways, so you'll have a great confluence of what we see on Mars with this rover when we're looking at what's in the distance and when we get up close and look at the fine scale of the rocks that we're collecting. And all of this leads to picking out those rocks that we want to core and cache and potentially bring back to Earth. This has been a very involved process. Lots of proposals came in. We have a payload that has a great international representation and well over 50 institutions worldwide involved. And I think it's going to be a fantastic mission. We're going to learn so much, and can't wait to really get going on the whole thing. And to put that all into context, I would like to turn it over to Ellen Stofan.
Thanks, Mike. Mike's really just described an amazing set of instruments that are really going to take our understanding of Mars to the next level. And we're really excited about that. If you think of our exploration of Mars going all the way back to Mariner, through Viking, the orbiters, the landers that we've had, we've built up this incredible portrait of Mars as this potentially habitable world. 2020 will take us the next step, making more sophisticated measurements to really try to understand this fundamental question that drives so much of what we do at NASA. Are we alone in our solar system, in our universe? The other reason we're so excited about this payload is because it includes elements from human spaceflight, from space technology that are going to help us take those next steps towards getting that astrobiologist, that geologist down onto the surface of Mars. So I can't wait. 2020 can't get here soon enough. Thank you.
Thank you all. Okay, so let's transition into the Q&A here. And I know we have a number of media on the phone, and I'm sure social media is a buzz, but we're going to take a question here in the studio first with Frank Mooring from Aviation Week. Frank?
Thank you, and sounds interesting, an interesting set of instruments. For the scientists on the panel, I'm interested in how the Curiosity rover findings will shape where you decide to land, how they shaped also the instrument selection. And I'm not really clear based on what y'all have said. Are you looking for, when you say signatures of life, are you looking for past life or any life, including current life?
Okay, so the first part of the question is how is Curiosity informing this 2020 mission? Well, certainly you might recognize that there are two instruments that look similar that are on Curiosity, and they're improved and super improved. And so part of that is, yes, this instrument has actually been very useful, and it's great that we get a proposal that we can use a more, better instrument for 2020. So we're in the process of exploring now of understanding not only whether or not the different environments that we're exploring could have supported microbial life, but a step further in understanding the environments that might be able to preserve a biosignature. This is actually a much harder problem. And we're going through that process. We're able to detect organics with the SAM payload on Curiosity, and that's going to inform us what would be really interesting places to go to in the future, what might be, what mineralogy can we see from orbit that might tell us this would be a great place to go and look. And so that's being fed into the whole process of the science community involved in landing site selection, that sort of thing. And the next meeting will be sometime in May, I think. So all that is an iterative process, and that's going to help us very much. I forget what the second part of that.
I think you've addressed it, but if I could do a question for Bill Gerstenmaier, could you elaborate a little bit on how the ISRU is going to work, and particularly what's going to happen to the oxygen after you generate it?
Yeah, at this point, what we're really interested in is operating a device on Mars to go ahead and pull the oxygen out of the atmosphere. And we can do that. We do that on board Space Station today, where we can pull some oxygen out of carbon dioxide through a Sabatier reaction. This is a slightly different reaction. But the idea is, are there unique things on Mars that drive us a different way? Is the atmosphere interact at all with the equipment that we need to understand? Is the partial gravity environment change ways? We want to look at oxygen production rates, understand those kind of things. And so it's not so much we're going to actually use the oxygen, but can we actually generate the oxygen? What kind of rates can we generate it at? What kind of efficiency can we do? And then that affects mission design. So those are the general kind of things that we're trying to look at with this in situ resource utilization device, because it really changes the dynamics. If you can get propellant or get oxidizer rather to be for your ascent stage to come off of Mars, and you don't have to carry that with you, that really changes your mission design. If you can actually cache and put oxygen in storage tanks before the crew even arrives, and you know they have a habitable environment and place to go when they get there, that's tremendously important to us. So what this will do is this will buy down the uncertainty of that. It'll make sure that we understand the risks associated with that, and we can do the appropriate planning as we look forward for human missions eventually to Mars.
Okay, let's head to the phone lines. And our first question, I believe, is from Seth Bornstein from Associated Press. Seth?
Yes, thank you. And this is just a follow-up on Frank's question to Gerst. You're looking at in the oxygen creation, for when you're talking about rocket fuel, that's only half the battle here. In terms of what are you looking at for the other part, especially in situ, for kerosene, liquid hydrogen? What are you looking at? When would you be testing this? And how far off are you talking about for an actual in situ fuel if everything goes right? I mean, are we still talking 2030s? And a secondary question, I guess more for Mike Meyer, is I want to make sure I'm right. You're not caching the rocks at all in this. I mean, nothing is stored with 2020. You may cache later, but not now, right?
So I'll answer.
Yeah, go ahead.
I'll answer the first piece, and then Mike can pick up the second piece. I guess where we are is this is kind of the first step to go look at oxygen. We'd have to look at other things. We've also seen, water on Mars, so you can clearly electrolyze water and make hydrogen and oxygen out of the water. So that's a resource, and you can potentially even use the water itself. And we also know there's nitrogen available in the Martian environment. So again, nitrogen can be a source for plants and other things that you may want to grow in the vicinity of Mars. So the first step was let's take a look at oxygen. We'll think about these other things as we go forward. Again, what we can do through a more sophisticated reaction is it happens on station. We take the hydrogen and the waste carbon dioxide on board Space Station. We combine those. We generate actually more water. And then the waste product of that is methane. Well, it turns out methane is a nice fuel for rocket propellant. So there's another chemical reaction we could look at in the future to do the fuel side to be compatible with the oxygen side. But the first step was, before we go pursue all these things, let's take one that's fairly simple, that can fit on this package, can fit on the rover. Let's see what the efficiency are. Let's understand, is there something we're really missing in the Martian environment that drives us a different way? Let's see what we can do with oxygen first, and then we'll do the plans for the other pieces as they fit together. And then I'll turn it over to Mike to answer the second piece.
Seth, we are definitely caching samples. In much of the way the instrument complement was designed was, in fact, to identify those things that would be most important to cache. The only reason I said for potential return is because we're not committed to returning those samples at this time. But it's definitely caching a sample. Part of it is it's a small delta to the cost of doing the mission, and it also helps us work through all the vagaries of how to cache a sample, how to seal it, how to do it properly, how to meet the planetary protection requirements, all those things that are some we haven't done before. And so we have the opportunity, we can cache these samples, and then at a later time decide whether or not those are the samples that we want to bring back.
Okay, we're going to take another call, and then we're going to see what's up on social media. Mike Wall from Space.com. Mike?
Yeah, hi guys. Thanks for taking this call. I think I would just follow up. I mean, I think Seth kind of blended this out when it was moving on to me. Where are you guys going to put the samples? Do you carry them around in the rover, or is there some spot where you're going to put them? And I guess, like, as a secondary question, could you just go into a little bit of detail about how you are going to actually look for biosignatures? Like, I mean, could you detail which of the instruments would potentially be actually finding evidence of past life, and kind of how that would be done?
Yeah, actually, that's an interesting set of questions. You know, the first one, the caching, as you might imagine, we're still kind of early on in the mission design, and how exactly the cache is going to be is still being worked out. The expectation is that it is going to be on the rover. The samples will be cached, and then there is some debate whether or not we drop the cache and the rover goes off and does its own thing somewhere else, or whether or not it just stays with the rover the whole time. There's even discussion of whether or not there's actually like two sets of caches where one is dropped off early and the mission continues while the 2020 rover is looking at a different region or different area of where it landed. So that's still in flux. I think obviously soon we're going to be setting the requirements for the mission, and within a little bit over a year we'll have our, basically review of, okay, here's the mission design, this is exactly how we're going to do it, and then it gets down to the nuts and bolts. Okay, so how do you look for biosignatures? That's not so easy. It's difficult here on this planet, and we know a lot more about it than we do Mars. So part of biosignatures, in fact, we kind of picked that word because there are different things that can clue you in that you might have something that is evidence for past life. And a good example is a stromatolite. You may look at a rock and see this layering that is suspicious looking, and it could be a structure that is left by an ancient microbial mat, or it could just be layering, and you don't know without investigating further. So how would you go about approaching this? Certainly with our massed instruments, you look around the landscape and you find those things that look most interesting. You look for mineralogies that might be best at preserving biosignature, at best at preserving organics, that sort of thing, or a recent outcrop, so that you're looking at some rocks that have only recently been exposed and less weathered by the radiation environment. And then with your turret instruments, the ones on the arm, you can now look at your samples at a much finer sample, the rocks at a much finer scale, to see if you have different minerals within the same rock, whether or not you have interfaces that might be particularly attractive for microorganisms, or representing a past environment that could have supported microbial growth. And that's when it gets kind of interesting, because then on the fine scale you can actually tell a lot about the history of the rock and whether or not it shows promise of being a place that could have supported life once upon a time, or something that even preserves some signature of that life. And then it's at that point where you would decide whether or not you want to drill that rock, take a core, and cache that sample for posterity. And that's how you go about it. It's not you don't have boxes to check. It is actually a real science debate in terms of when you look at something, trying to decide what it is you really do see. And so one of the fun things about these missions is the weekly science getting together and debating what is it that you think you found, and sometimes, not always of the same opinion, and that makes the discussions even more interesting.
Let me just add that because it's so hard, even on Earth, to figure out whether, a rock, a mineral, is a signature of ancient life on Earth. And of course, the Earth has processes that bury most of the interesting rocks, but we have a few examples. Because that's so hard, the suite of instruments we've put together are our best shot at trying to identify those places on Mars, those little bits of rock that look the most promising. And it's also the reason why we have the cache, so that we can then take a core of that rock, put it into a little sample jar, store it, and then someday get it back to Earth, where the best instruments on Earth that scientists have are really going to be able to confirm it. Because as Carl Sagan said, extraordinary claims require extraordinary evidence. It's really going to be when we have the best analytical instruments and our ability to interrogate these samples at the smallest scales with the best instruments that we may really then be able to say for sure whether or not Mars once had life. Now, if we see, a trilobite on Mars or a fossil that we recognize, that's going to be really phenomenal. But and for that we have imaging instruments, but we're not expecting that.
Yeah, and just to add to it is, we have multiple ways of actually detecting organics, and so finding organics associated with a particular mineral can be very exciting, and that's where you figure you really hit the payload on that one. So
Michael said,
the capability is there.
Now that we have the suite of instruments, the project team can actually go and design the caching system. Until then, we just had various designs that were notional, but with this complement of instruments, one of the good news stories is that a relatively straightforward, simple cache is likely where we'll go, because that's the right answer. And that also allows us to have this great suite of instruments that we selected.
Okay, before we go back to the phones, we're going to go to social media and keep those questions coming at #AskNASA and join the conversation at #JourneyToMars. We're going to go to Jason Townsend, and just a note that we obviously will not be able to get to all your questions, but we'll have some of our senior scientists answering your questions throughout the day following this press conference. So keep those questions coming in. A lot of conversation on Mars. Jason, what we got going?
Sure. There's a lot of interest here online about how this rover, the 2021, compares to Curiosity. So a couple of related questions to that. Jamie asks, is the 2020 rover the same size as Curiosity? Matt asks, will the 2020 rover be landing in the same manner as Curiosity? And then Joe asks, what kind of speeds is the 2020 rover capable of achieving?
So the answer is it's the same architecture. So the rover is about the same size. Obviously, since there's different instruments on it, there'll be a little bit of a variation, but essentially the payload, the landed mass is going to be less than a metric ton. It's going to land in the same manner using the sky crane, that sort of thing. And in fact, from what I understand, the limit to the mass that can be landed is in fact the wheels and the structure itself. And so that's set. So we don't have to debate that. We just have to fit within those constraints. The speed Interesting question. It's not very fast, and one of the things that slows us down now is after covering a distance on the order of something like 30 meters, the rover has to stop and re-image everything and see whether or not there are hazards in its way and compute a safe path and then go another 10 meters and do the same thing. But the first 30 meters is determined basically back on the ground of looking at your terrain and where you can go. So one of the advantages that we'll have with Mastcam Z, by being able to zoom and looking binocularly, is we'll be able to plot out a greater distance for the rover to go initially before it has to then start calculating how to take the next 10 meters type of thing.
All right, we have a couple of questions that have come in from our Ustream feed here. That one of them asks, why is finding minerals important?
Finding minerals, that is the rock. That tells you how the rock was made. Knowing that the rock has certain elements in it or helps you understand what the rock is, but the mineralogy is how the rock was made. A good example is if you're getting engaged and you're going to buy your fiancée a ring, giving her a lump of coal versus a diamond makes a big difference. They both have the same elemental chemistry, but one is a rock, and one is coal, one is a diamond, and all that is the environment that piece of carbon went through. And so that tells you something very important about the history of that rock, knowing its mineralogy.
Essentially, let me answer.
Yeah. I was just going to say, some minerals, for example, require the presence of water to form. And obviously, we think water is really critical for life. And so mineralogy really gets you at not just the history of the rock, but the history of the region the rock was formed in. And water is certainly something that we're really focused on.
So those are the geologist's answers. But the bottom line is finding minerals is not really what it's about. And what this rover is going to do, it wants to look at the rocks on Mars. And the rocks on Mars tell a story. And they tell a story about the history of Mars. They tell a story about whether Mars was once habitable and whether Mars once had life. And the words in the story are written in minerals. And that's what this rover will do, is it's going to tell us what the words mean of the history of Mars and the story of Mars.
One more, Jason?
Wonderful. Alexandra on Twitter asks, what wavelength is being used for the Raman on SuperCam?
The laser is, I think, a 532, yep. So it's kind of greenish.
All right.
Okay. Keep those calls coming in, questions coming in at hashtag Ask NASA. We're going to go back to the phones now. And I believe we have up next Eric Hand from Science Magazine. Eric?
Hi, yeah. Can you hear me?
Yes, sir.
Thanks for taking the call. Quick specific question and then a follow-up. What is the payload mass and cost?
Well, this is really one of the most amazing things to me, is that the Curiosity rover is about a metric ton. I think it's close to 950 kilograms or so to the surface of Mars. And this rover is, as a rebuild of the rover chassis with new instruments, will have about the same mass to Mars, about a metric ton. And this just gets back to it's really hard to get to the surface of Mars at all. And just the infrastructure, what you need to support a rover, to have a radioisotope power source, to have wheels and an arm, takes up a lot of that mass. And so in the end, we're looking at somewhere around 40 kilograms of science instruments to the surface of Mars. And it sounded to me crazy at first. Turns out that's a lot of science mass to the surface of Mars, and we're very excited about that. The total cost of the mission, we're working towards a target that's around $1.9 billion, which is substantially better than we did on Curiosity, because that was the first time we built it. And so now we've done the systems engineering already to be able to reproduce the rover. Plus we have spare parts left over, and as a result, and we don't have to do development engineering on some of the parts that we do have to procure. And so that's allowed us to streamline the process. So that's the target we're looking for. For the instruments and the in situ resource utilization, our U.S. investment is going to be about $130 million.
I believe we have on the call next. Eric, did you have a follow-up?
Yeah, please. Let me work up to a question. I guess my comment is, so the payload mass is 40 kilograms and Curiosity's was 75. So, I guess I wouldn't describe 2020 rover as an amped up version of Curiosity, but rather a stripped down version of Curiosity. And I understand the reason for that, and that is the need for a cache. And I also understand that the real search for biosignatures would one day happen on Earth. But, I guess I wonder if you have a comment, without a mass spectrometer and an oven like you have on Curiosity, which is what takes up the bulk of that payload mass, how can you describe this as a mission that searches for organics and biosignatures?
Let me start, and then I'm going to hand it over to Michael. There are actually a number we didn't describe as the overall changes to the rover. And for instance, we have 2 instruments on the arm of this rover, but we're also going to have a rock abrasion tool that we don't have on Curiosity. So we've changed some of the infrastructure, and as you mentioned, the cache. But from a measurement perspective, it's true we don't have a mass spectrometer in the ovens and the sample handling system and those kind of things associated with the sample analysis at Mars Instrument that's doing just amazing work on Mars today. But from a measurement standpoint, with these new measurements, the 2 lasers, the Raman, the enhanced mineralogy, the enhanced imaging, this really is a souped-up instrument suite compared to Curiosity. And the 2 together, and especially if we get to look at 2 different diverse sites on Mars, may be completely transformative. But I'll hand it over to Michael.
Yeah, every single instrument is either improved or we haven't sent it to Mars before. And the real trick to this payload is that we get to look at the fine-scale spatial distribution of these things. One of the unsatisfying things about having the analytical lab on Curiosity is you take your sample and you grind it up and you basically get a bulk number. It doesn't tell you the relationship between each of the minerals that are in that sample, or if the organics that you measure are associated with one mineral versus another. So in many ways, we do a trade-off of looking at the fine-scale mineralogy and elemental composition, seeing how that's done spatially, knowing whether or not the sample is really interesting, and then when we bring it back, if and when we bring it back to Earth, then we could look at the spatial relationship of all these things at an extremely fine scale because we have the instrumentation and the sample handling capabilities back here on Earth. So I consider this a real improvement in all the instruments that are on board and also what potential science this rover can do is certainly more than what Curiosity can do right now.
Okay, we've got about 10 minutes to go here, so we're going to try to get in as many questions as we can on the phone. Next up, I believe we have Dan Leone from Space News. Dan?
Really interesting discussion. I'm curious, when are you going to settle on the requirements for the rover? And is it possible that sample caching could be excluded as a requirement for any reason? And I have a follow-up, too.
So about a year from now, we'll have the final requirements. Now that we have the suite of instruments and we can define the caching system and the continuing work that's been going on by the project to get the rover going, we'll have all those requirements. There's always the possibility that the caching system gets de-scoped if we run into trouble. We're hopeful that's not the case. I guess I should say from the start, though, your opening comment, I'm really glad that you're curious about this because this is just one of the greatest things that we're doing right now in planetary science. And sorry, the rest rest of your question?
Dan, did you have a follow-up? Okay, let's go to the next caller, Leo Enright from Irish TV.
Thanks, Dwayne. I'm sorry for lowering the tone of this conversation, but I'm a pictures guy, and I'm just wondering how the imagery will compare with what the extraordinary pictures that we're getting back from the Mastcam on Curiosity. And in particular, there was a lot of talk before Curiosity was launched about a 3D movie camera flying on that mission, with James Cameron and Mike Malin were working on it. Was that considered or not?
The Mastcam zoom is a stereo camera, and with the zoom is just going to knock our socks off with our views of Mars. This is going to get so much closer to being able to have the experience of a human with two eyeballs separated by about 6 centimeters. When we look at the images that are going to come from the Mars 2020 rover, especially if you take a sequence of stills and put them together into a motion video, you're going to feel like you're on Mars. It's going to be fantastic.
So just to add to that, if you look at the graphic of Mastcam, over on the left-hand side are the two cameras that are on Curiosity, and one is a 34 millimeter focal length and the other is a 100 millimeter focal length. The idea is that you don't have to have those focal lengths if you have a zoom, and so you'll still have binocular vision, and you'll still have the capabilities of both those cameras, except for it's incorporated into, they'll both be able to see the same thing, either up close or far away. So the basic answer is you'll still get spectacular panoramic views of the same resolution that we're getting with Curiosity now with Mastcam, but with the zoom capability is going to give you a much different feel of being there in place and be able to go up close and personal to something at a great distance.
Okay, we're going to take one more question from the phone. We're going to come back here and one more question on social media. And a reminder to the media and the social media also, at 3 p.m. Eastern, you'll have an opportunity to talk to the principal investigators. There will also be Mars senior managers there to answer the questions we don't have time for here. So again, 3 p.m. Eastern, there'll be an announcement shortly coming out from headquarters with information on that. So on the phone, we have Lisa Grossman from New Scientist. Lisa.
Hi, thanks for taking my question. I was wondering if there's any more development on how we're going to get the samples back, and also if we have to send something later to go pick it up, what's the usefulness of catching something now and of storing samples ahead of time instead of having the next thing go pick up samples immediately and then bring them home in one go?
Well, what we're announcing today is really our next big leap in the exploration in our journey to Mars. And that journey doesn't end with one rover, and that's why we're sending a second rover, Mars 2020. It's a big planet, a lot to explore. And so this is really just the first step in understanding the planet with future missions, trying to get humans, especially astrobiologists and planetary science, to the surface. And I wouldn't rule out the possibility that it's a future astronaut that picks up the sample and brings it back to Earth. But that's forward work. We haven't defined that. The first most important step, though, is to find samples that are so compelling that we need to get them back. And that's the purpose of this rover, is to be able to read that story of Mars and identify, are there some samples that are so compelling that we would want to get them back to Earth? And it may not have been clear in the discussion, I just realized that how are we going to get those samples? And so on the end of the arm is a drill very different from Curiosity. Michael Meyer described it. The drill on Curiosity grinds up the rock, puts it into the rover, analyzes it. For Mars 2020, we have a coring system, like taking a core out of an apple. It's going to core into the rock, preserving a little cylinder of rock just as it is on Mars. And it's that preserved, pristine sample that we might eventually bring back to Earth.
And to follow up on, well, are you worried about the cache sitting there with the samples in it? And we've had some science teams looking at this, and it's actually, as long as it's sealed, it's not a problem, and we think that the sample can be very stable for at least 20 years. So taking a core out of the rock and putting it into something else in which you protect it from the environment is fine, and it will be stable there until we go and decide to go and get it.
Okay, so Jason, you're going to take us out here with a question, and then we're going to see if we have any closing remarks, and I'll give some housekeeping notes. So, Jason?
Wonderful. Several people have asked on both Twitter and on our Ustream feed and other platforms here regarding the wheels. So Corey here specifically asks, what improvements to the 2020 rover wheels, if any, will be made on how Curiosity's wheels have managed?
Well, this is one of the great things about operating Curiosity on the surface now, is we're learning how to drive on Mars, and the driving team is doing a great job. And the team that spotted that the wheels were cracking, was also really important. And having imaging that can look at the wheels is an important part of that. And so we've been driving over really rough terrain, and it's causing these cracks, we believe. And there's a rover in the Mars Yard at Jet Propulsion Lab that's practicing and trying to reproduce these things. And if you look at the treads on the Curiosity rover, they were designed to provide traction, but also to prevent cracks from growing in a certain direction. And so the team's now actively working at redesign of the wheels, in part to look at, can we choose alloys or structures that are still lightweight but wouldn't crack as easily, but also new structures that would prevent those cracks from growing. So that's a very active area, and we could ask the project folks here if they wanted to elaborate. But that's something that we're going to fix, and also we're going to try and plan when we get to the site. We first have to pick the landing site. We're going to try and be a little more careful about where we drive and avoid those curbs.
Okay,